So thanks for the introduction. So JP mentioned I'm Brandon Wilfong. So those who had the hydrothermal practical so far, you've already met me, and I've kind of given you a very brief rundown in the practical about hydrothermal synthesis. So this is essentially just to give you some more background on the background of hydrothermal synthesis and how we think about actually doing hydrothermal synthesis from a first principles type of idea. So again, not Efren Rodriguez, but so acknowledgements. This is our group. This is an older picture. I don't know if we have a picture with all the new students, but basically these are all the grad students and postdoc. This is Efren here. But a lot of this work is later done by, previously by our grad student Zhixuan Zhou, who's a postdoc now at Argonne National Lab, me, and then our third year grad student Huafei Zhang. And of course, thank all our collaborators as well. Also acknowledge all the funding sources, so Efren would appreciate me doing that. So hydrothermal vents in nature is actually a really, really cool topic. So that's where the idea of hydrothermal synthesis kind of started at. So basically, these are in the seawater. There's hydrothermal vents in like the Marianas Trench, for example, where you have seawater that comes in from an ocean or a sea. And that comes in contact with some hot source like magma under the Earth's crust, and then basically because you have only these intrusion zones where only so much water can flow through, you start to build up very, very high pressure as the water comes in contact or in close proximity to your very, very hot magma. And then in these regions you can start to have very, very interesting chemistry and different reactions start to happen where you have some iron-rich ore or some more exotic minerals that can start to form at these interfaces, and then those get pushed up depending on tectonic plates and things like that. And there's a lot of active research, especially in the realm of how life started on Earth, and a lot of research going on to see what kind of new bacteria and different minerals can be formed at the interface of these hydrothermal vents. So that's one really cool kind of separate part of research on hydrothermal synthesis in general. So all the stuff you've heard today and the past couple days about single crystal growth, hydrothermal is the best way to grow single crystals. Maybe not of what you want to make, but you can see this is a 6-foot man, or maybe an average 6-foot man, and you have crystals that are much, much, much larger than he is. So if you were able to grow crystals this big in your lab, if it was something like uranium ditelluride or something very interesting, your PI would be very, very happy. I'm not sure what kind of furnace or whatever you'd have to have, 29 foot long, but you could do it if you had the. Right, that's probably true. Yeah, some safety concerns surely. But this is large gypsum crystals in a cave mine in Chihuahua, Mexico. So you can get very, very large single crystals made from hydrothermal synthesis. So this was a YouTube video that got cut because I'm only giving a 30-minute lecture, but I'll leave it up on the slides for when you go. I think it's like 15 minutes, a very old lecture from It's a video from Bell Labs about how they do quartz single crystal growth. It's very, very cool. It's very, very old, so it's like shot in like sepia tone, but it's very, very cool. So if you had time to watch it when you get back to your institutions, I'd really recommend it. So this is just some other crystals that can be grown through hydrothermal. So again, this is quartz crystals grown at Bell Labs, and this is the world's largest autoclave in Japan, Toyo Communications, where again they're growing quartz. So quartz is like one of the main things that has historically been grown with hydrothermal method, and again you can see these crystals are as big as the guy's head. So again, you can get very, very large crystals from hydrothermal synthesis. So again, some history. So this is one of the Robert Laudis. This is one of the pioneers in hydrothermal synthesis and actually using hydrothermal synthesis effectively to grow materials that are used in industry. So he was the inventor of the quartz crystal growth process using hydrothermal autoclaves. So this was just a really good quote where basically he's getting at the point that if you lose the ability to have a material, everything that follows from the material, so if you use quartz for some communication device, everything else is null. So the ability to have and grow a material that's industrially important is the first principle to thinking about how we can actually use those materials later. So here's the outline for my talk. So I'm going to give you some basics about hydrothermal. So for the ones who have had the practical, it's kind of a synopsis of that with some expansion on some different topics. I'm going to talk briefly about the physical chemistry of hydrothermal synthesis, tell you about autoclaves, and then give you a couple slides on the application that we actually use hydrothermal synthesis for the synthesis and characterization of iron-based superconductors. So the basics of hydrothermal. So just for a formal definition, basically there's a bunch of different definitions, but the commonly accepted one today is it's any synthesis or reaction above 100 C and 1 atmosphere, and it's done in water, so that's why you have hydrothermal. There's a lot of other related terms, so if I start throwing in different related terms, I'll have the definitions up, so you don't feel like you're getting lost. So there's also solvothermal reactions, which basically is the umbrella term that covers all other hydrothermal reactions without water. So any other solvent. So the most popular ones are, ammonia, some alcohol, ethylene glycol. All those would be considered solvothermal. So if you see solvothermal used in literature, basically you have to look at what solvent they're specifically using because it's not water. And then the mineralizers is basically your solvent. So sometimes they don't call it a solvent; they'll call it a mineralizer, especially in geochemical literature where they use a lot of hydrothermal synthesis or hydrothermal method to manipulate their samples. So basically, it's just whatever your solvent is that dissolves the solid, such as a mineral. So that's why it's used. That's why the term mineralizer is used. So these are just some broad strokes, advantages and disadvantages. So the one really big advantage is that it's low temperature. So for a lot of the stuff that we do in our lab, because we're using Teflon liners and things, that we're limited to below 300 C. So for the equipment we need is very, very simple, more or less. And the other thing that's really nice is that because you're at lower temperatures, at high temperatures, so a traditional like flux growth or something like that, you're always making the thermodynamically stable product because you're going to such high temperatures that you're going over the activation energy and you're always forming the thermodynamic product. But because we actually do these syntheses and modifications at low temperatures, we can make metastable phases. And what that means is that if you're trying to form a phase that has a certain structure you want, but it's not on the binary, ternary, quaternary phase diagram, you actually might be able to form it using hydrothermal synthesis or some other soft chemical technique because we're actually doing low temperatures. And that's because there's two guiding principles in thinking about what's going to form your products. Thermodynamics, which I mentioned before, so high temperatures, you're always going to get the thermodynamic product. And then at low temperatures, you're allowing kinetics to become involved. So if you can kinetically control what products are being formed, you can actually make metastable phases. So lower concentration of defects, that happens because at high temperatures, you basically, any defect has a energy penalty, but entropy starts to win at high temperatures, so you can form defects. But at low temperatures, you're not taking on that energy penalty to form the defects, so you actually have lower defects overall at these low temperatures used in hydrothermal synthesis. And then low energy process, cheaper. Basically, for the PIs in the room or postdocs who are thinking about becoming PIs, all the equipment you need for hydrothermal synthesis, like the autoclaves themselves, range between $500 to $1,500. And then the ovens we use, because we're only going to 300 C at most usually, they're on the order of $5,000 max. So to get a working setup for all the stuff you need for hydrothermal, you're looking at below 10 grand. Versus if you're trying to do a high temperature solid state synthesis at 1500, just the oven alone is going to be 20, 30 grand. So much cheaper to think about the type of equipment you might need for hydrothermal synthesis. So there's a lot of different materials that can be prepared. A lot of literature on these different things like native elements, especially metal organic frameworks. A lot of metal organic frameworks are made through hydrothermal synthesis. And then inorganic hybrid materials. A lot of these you can make because of the fact that we're using kinetics to control our product as opposed to thermodynamics. So in the hydrothermal synthesis, what mediates your crystal growth is the solvent itself. So the viscosity affects the diffusion. So you can think about the fact, think about water versus maple syrup. Maple syrup is much more viscous. So if you think about how solute molecules might flow through maple syrup versus water, they would flow much slower, which affects your crystal growth. And another thing that's very important to think about from a chemical point of view is dielectric constant. So high dielectric constant allows for the dissolution of your solids. And you got to remember from Gen Chem, for those who took Gen Chem, like dissolves like. So if you want to dissolve a polar solvent, if you want to dissolve a polar solid, you're going to need to use a polar solvent. So that brings me to water. So water is considered the ultimate solvent, essentially. So this is just what water looks like in the dielectric constant. So basically you can see that at hydrothermal conditions, the properties that control crystal growth, the viscosity and the dielectric constant, actually change drastically for water. So you can see at room temperature, all of you know that water is a polar solvent. So at room temperature we see our dielectric constant here is very, very high, right? So it's a polar solvent. But you can see as we get to very, very high temperatures, the dielectric constant actually approaches unity. So it actually becomes nonpolar. So you can actually use hydrothermal synthesis and water specifically to do nonpolar chemistry at very, very high temperatures if you're able to achieve those temperatures. And you can see also that the viscosity goes way down. So you actually can, control the crystal growth in some way by controlling the temperature. So these are some other solvents that are used and just their boiling points and dielectric constants. So if you needed to, tune, if water wasn't working and you needed to tune different polarity or dielectric constant, these are just some widely used ones: DMF, DMSO, ethylene glycol. They all have their different safety concerns that you need to consider, of course, but they're used pretty frequently. So is hydrothermal a high pressure technique? Overall, for the stuff that we do in our lab, it's not very high pressure. So this is the number one, this is the thing that we consult a lot. So it's pressure as a function of temperature, and all these different lines are different filling fractions. So it's basically if your autoclave or the system you're trying to fill has a certain fill rating. So let's say it's 25 milliliters. If you fill up to a certain amount, that filling fraction percentage is what you see here. So basically you can see that at low temperatures, so a lot of our stuff is done between 100 and 200, the pressure is very, very low, and it doesn't really change depending on your filling fraction. But if you start to go past the critical point of water, or if you approach high filling fractions, you can very, very fast go up to different, higher pressures. But I mean, we do, as you see here, or bombs. So autoclaves, we do colloquially call them bombs. So that's how I know an FBI agent isn't watching my phone, because I text my colleagues and say, did you recover the bomb? Or how was the iron bomb looking? So if there was, I would be on some watch list by now, but I'm not. Well, at least I don't think I am. But basically, for more or less, for the stuff that we do in our lab using Teflon liners and the PAR type autoclaves, which I'll discuss later, we're in this regime at very, very low pressures. But if you have a hydrothermal furnace or more sophisticated hydrothermal autoclaves, you can go up to very, very high temperatures, and then you can start approaching pressures that become, much, much higher than atmosphere. So this is just a, cartoon drawing of what a traditional hydrothermal growth would look like. So basically, you have your nutrient. Which is basically your starting solid of your reagents. It sits inside your mineralizer in the liner. So basically this shell is what's going to hold everything together, and your liner, your inert liner, is what's going to hold inside the shell. So I put inert liner because you hope that your liner does not react with your reagents, or else you're going to have a problem later on. And then the mineralizer would essentially dissolve that nutrient. So usually we use water, but of course you can use any solvent. And you tune that to be acidic or basic depending on what you need for your reaction. And then in the case of growing quartz, you can actually set up seed crystals that sit at the top so that you can grow your quartz single crystals from those seed crystals. So I'll talk very briefly about the physical properties of hydrothermal synthesis. So the actual physical chemistry, like thinking about the thermodynamics, the critical behavior of water or different solvents, is still an active field of research. So basically, the studies of aqueous solutions at high temperature, high pressure, especially what you would approach at, in those sophisticated hydrothermal autoclaves, very, very high temperature and pressure, is still being researched. And then a very specific field that's being researched very heavily also is the study of the actual crystal growth at hydrothermal conditions. So one thing that a lot of people don't like, or it's a downfall of hydrothermal, is that they call it a black box reaction, because you basically put everything in the liner, put it in the shell, close it up, you put whatever you put in, you don't know what happens in between, and you take it out and then you're good. But there's a lot of different work being done to try to study exactly how the crystals grow in the hydrothermal autoclave using in situ X-ray diffraction or in situ neutron powder diffraction, that sort of thing. So I'll just talk very briefly to kind of motivate the thermodynamics and how these crystals are actually, how the thermodynamics is used to grow crystals. So during the crystallization process, basically you have a saturated solution, and you have a number of moles of your solute changes. So you have to use the grand canonical partition function, or the grand canonical ensemble. So I'm not going to start doing a ton of stat mech, but just if you remember from your stat mech class, basically your Gibbs free energy is a function of temperature, pressure, and then all your different constituents, and they're allowed to change in this. So if you do you think about your partial Gibbs free energy, For our system, if we're considering equilibrium, so we put the reaction in and we let it sit at the same temperature and the pressure is built up and is at equilibrium, your dT, or your change in temperature, is 0. And your change in pressure is at 0. So we're basically at equilibrium. So all of your Gibbs free energy actually only depends on the number of particles of your solute and solvent that are changing. So if we simplify that, basically our Gibbs free energy, if we expand it, let's say we have a 3-component mixture, basically a solvent, a solute, and then that solute as it gets dissolved into the solution. So we say A is the solute, B is the solvent, and then A1 is that solute as it's actually in solution. So if we assume that the solute is being dissolved, the number of moles of solvent or solute are going down, and then that number of moles of diluted or solvated solute is increasing. So basically you just decrease here and the same amount are going into solution, so you increase here. So that can be reduced here. So because basically we're assuming that the solvent isn't participating in this case. That's not always a good assumption because sometimes your solvent actually is being used to form your crystal. So in that case, this can't be simplified this way. But in the case where your solvent is just acting to mediate your reaction, you can actually get rid of this term. So basically your Gibbs free energy just comes down to the chemical potential or your activity of your solute and solvent. Or sorry, solute and your solute as it's being dissolved. So basically if you simplify that even more, you basically see that your Gibbs free energy depends only on the activity or your chemical potential of your solute as it's in solution and your solute that's not in solution. And what you see is that in the case that your activity of your chemical potential of your solute in solution is greater than your solute out of solution, your Gibbs free energy is negative. So this is a spontaneous process where A dissolves into B. In the case where they're equal, you're at an equilibrium state and nothing's going to happen. But in the case where the chemical potential of the solute in solution is greater than your solute out of solution, then that's non-spontaneous and A will actually crystallize from B. So what you do is you set up a reaction where both those conditions are met at different parts of your autoclave. So basically, this is again a schematic of a hydrothermal autoclave where you have your charge zone that's set to a different temperature so that this condition is met where A will dissolve into B, and then you have your growth zone with your seed crystals, which is higher up, which you set at a different temperature so that this condition is met where A will precipitate out out of solution into the seed crystals. So this is exactly how quartz is grown, where you set up a thermal gradient where the chemical potentials for the different things are different, which allows for dissolution in one zone and then precipitation in another, where you can actually grow large single crystals. So again, I've mentioned this slightly before, because it's people think of it as a black box reaction. The kinetics of the crystal growth is not very well understood, but it's still actively studied. We actually have a collaboration with 17BM and Argonne National Lab where we do in situ hydrothermal powder diffraction, where we actually set up a hydrothermal reaction in a quartz tube and then do 3-day runs where we'll take a X-ray image every 5 minutes and just see how the different intermediates are being formed and how the crystal growth happens. But it's still an active field of investigation. So then autoclaves. So yeah.
So rather than setting up a gradient, would you also consider just changing the temperature?
Yeah. So you can do that as well. You can basically you can set up a gradient where you have a charge zone and a growth zone, or you can do the opposite, where you set up to one temperature where it all dissolves, and then you can slow cool out of that, where you have dissolution happening at one time frame and then growth happening in another time frame, where you can. So if you don't have a 2-zone furnace, for example, you could do it that way. So the properties of an autoclave that are typically, a necessity, you need to have inertness to acid and bases. So a lot of the solvents that you're going to be using is water, and then if you're thinking about what different chemicals you're going to have in solution, you're going to need to use acidic or basic chemistry. It needs to be easy to assemble, so you don't want to be spending, a whole day just trying to get the autoclave together. So for temperature gradient growths, it needs to be of sufficient length to fit in your 2-zone or 3-zone furnace, or long enough so that your gradient actually is meaningful, so that you don't have just a null gradient if you need the gradient for growth. It must be leak proof. So the ability to achieve hydrothermal from the definition above 100 C and above 1 atmosphere, it needs to be leak proof, or else you're not going to be able to hold pressure. So it has to have well-known temperature, so you don't want to put something in that you don't know how it's going to heat up. And then, again, high pressure. It needs to be able to hold those high pressures as long as you know what pressure you're going to be getting to. So in our lab, we've never had a catastrophic failure of an autoclave, but I have heard of different groups where if they use the autoclave not how it's listed, essentially. They go up to too high of a temperature, or they put in a solvent that will build up too much vapor pressure, they can actually have catastrophic failure of the autoclave. So this is just a list of the different types of autoclaves that are used, the most popular. So in our lab, we have these two, the par type, flat type. So you can see we can get up to 400 and 200 to 350 bar. We actually do have a cold cone seal Tuttle Roy type, which I'll show you in a second, from a hydrothermal furnace. And then we do use Pyrex and quartz tubes. The big downside of Pyrex and quartz tubes is that there's no pressure release mechanism. So the pressure release mechanism of a quartz tube sealed is to explode. So if you're using a small quartz tube, it's not a big deal as long as you set up engineering controls to manage the explosion if it does happen. These are the most popular liners used. We almost always use Teflon because it's inert. The big drawback with Teflon is the maximum temperature is about 300. That's because Teflon starts to deform above 300, and then you start lose the ability to hold pressure. So if you do need high temperatures, like for the hydrothermal furnace, where you're trying to go to 800 at very high pressures, you need to use a different liner like titanium, silver, platinum. And then the problem with those is that a crucible or a liner made of platinum, if you're trying to have a large growth, could be thousands of dollars. So this is just the type of autoclaves we have in our lab. So for the practical, for those going to the practical, these are the exact ones we have. So if you haven't been there yet, I'll show you later today. And then again, this is the Tuttle Roy type. So the one before were the Moray type or flat type. So this is the Tuttle Roy type, where it's just a different, instead of it being a flat plate, it's a cone-on-cone mechanism that allows you to go to higher temperatures and pressures. So this is a hydrothermal furnace we have in our lab that was donated to us by a retiring professor, and one of our grad students, Stephanie, has done a lot of work of getting it fixed. But basically, the Tuttle Roy type fits inside of this cylinder. This is basically your 2-zone furnace oven that allows for your temperature gradient, and we can get to very, very high temperatures. So we can get up to 1000 C if we have the right liner, of course. 2-zone, and we can go up to 4.14 kilobar of pressure. So those, like a high pressure furnace, can be used for a lot of different growths if you have the ability to get up to these high pressures and temperatures. So this is just an example of temperature as a function of pressure that we've actually done using. We have a platinum liner, and we use that to get up to these temperatures. And you can see we can get up to 30,000 bar or psi of pressure, which is really, really high. And I'm running out of time, so I won't get to the applications, I don't think. But anyone has questions about applications, you can talk to me after, or for those who still have the practical to go to, you can talk to me about how we use hydrothermal synthesis to study the synthesis of iron-based superconductors. But yeah, I'll just show you some slides. Yeah, so one thing that we're interested in is the synthesis of intercalated lithium hydroxide iron selenide. So there's been previous work showing that they claim a ferromagnetic superconductor. So we have two different methods. The one where we call a bottom up, where we form it from the constituent elements, where we have lithium hydroxide, iron, a selenium source, and we react that for 5 days and make the product. And this method, we form powders because we're forming it from the constituent elements at low temperatures. And then we have another method where we form a related compound, the 1,2,2, potassium, iron 2, selenium 2, single crystals. And then we use that to do a cation exchange, where we actually exchange the potassium between the iron selenide layers for lithium hydroxide, and we can take single crystals of this material and make single crystals of the lithium hydroxide intercalated phase. And from there, we've done some X-ray diffraction and shown what the crystal structure is, and then we put together a phase diagram where you can show what the TC is as a function of crystallographic properties, depending on if you do the bottom-up synthesis here or the cation exchange synthesis here to make single crystals. So this is just exactly what the single crystals look like. I thought this was really cool when I first started, that we can literally take single crystals of some material and make single crystals of another material, and they don't change that drastically as long as the bonding of the layers isn't that different. So just summary. So a lot of work we're doing now is on that cation exchange of single crystals to try to make magnetic superconductors by design. And then a big focus of work is trying to make van der Waals heterostructures, where we're actually making layering different materials with different functionalities to make heterostructures that can be used for multifunctional devices. And I think that's it. Yeah.
Thank you.
Yep.